some interval over which you would like to find its area. Okay? You want to know the exact area under the curve. This is an extremely hard problem, right? Because in an arbitrary curve, the area under the curve does not conform to one of your well-known formulas for rectangles or circles or triangles or things like that, right? So a lot of times you're stuck with approximating until 5.3 or something, right? We're doing a lot of approximations right now, and the process can get a little involved sometimes, so try to follow. First of all, you must decide how we're going to break this up to rectangles. We're going to use rectangles specifically because we're going to compute areas of rectangles readily. So I want to break up this interval AB into some number of subintervals. Okay? So the letter N is the number of subintervals for the problem. We're going to break this up into in equal length subintervals. Every problem we're going to do, they are always equal length subintervals. Number of subintervals, and just as an aside, of equal length, making our task much easier. That equal length that they are broken into is going to be called delta x. Delta x is that equal length for each subinterval. All right, delta x can be computed though. That's just what it is. That's what it's supposed to turn out to be. It should be the length of each subinterval we're going to break this thing up into. So delta x though has a formula, and it makes sense that it should be b minus a on n. It should be the length of the interval. B minus a is the length of said interval. I'm cutting it into n pieces. So there is delta x always for us. B minus a on n.
Some intervals means are interval like, is it like a to b and then?
I'm going to cut this up into some number of smaller intervals.
Oh, that could be any number you want.
Could be, right. We're going to use natural numbers to do that. Right now it's cut up into one interval. I can cut it up into two intervals if I want. Right?
But isn't it like the smaller the length of the subintervals, the more accurate it is, something like that?
Absolutely. That's absolutely right. But the smaller length of the subintervals is more burdensome to computation. Because you have to add up more things, right? You're going to have more things to add up the more subintervals you have.
So since we're using a rectangle like type with that top piece, that like slope piece, would we use like a triangle, an area of a triangle for that? And then
We're not going to use triangles though. But you'll see. So just as a quick example, I'd like to break this one up into four subintervals. Okay? There. 1, 2, 3, 4. So each of these here is of length delta x. For delta x in this particular example would be the length of original interval divided by 4. That's what I've chosen. I wanted 1 to be 4.
So and it's just,
Could be anything. Depends on the problem. They'll tell you.
oh, so they'll give you that.
Yeah, usually.
Okay.
It's going to get more abstract in the next section, and we won't have a particular n to put in. But right now, yeah, I'm going to pick one for you. Okay, so now the idea is I'm going to draw rectangles up to here. These are actually the same width, they're all the same width, I just didn't draw very well. Now comes the question, how do I decide on the height of the rectangles? It has to do with the function values somehow. So the one I'm going to present at this moment is called a left endpoint approximation, right? Left endpoints. That's this particular first example, at least for the picture, left endpoints. So that means you start with the leftmost endpoint of the original interval, which is a in this case, and you go up to that part on the curve, which is f of a. F of a, right there. Okay? That is height of first rectangle. Height of first rectangle is f of first value in original interval, right? Starting at the left. So what that does now is that tells you the height of first rectangle. So now it draws down to there. So you see your first rectangle is over approximating the curve at this moment, right? There's more area to the rectangle than there is to the curve, which is within the rectangle. Agreed? So first rectangle is an over approximate. Happens to be the way I drew the curve. So now, since using left endpoints, that means for each subinterval, the left-hand side of the subinterval determines the height of that rectangle. So you start there now on the curve, go over here, and go down there. And again here, across here, go down there. There you go. This one will be a slight underestimate, right? Clear that out of there a little bit. Any questions so far? Just in terms of the construction of the problem. Left endpoints.
It looks so. It looks like that slope's it's going in towards the downward slope. How about if you have like a U type of slope where it's starting to move back up? Would you still take the endpoint and move it across? You see what I mean?
Say it one more time. This picture looks like what? Say it again.
It's like the points you have where the brackets are. It's on a downward side of the curve. You see what I mean?
It's on the downward side of the curve.
Yeah, like it's heading towards. Like imagine if you had one that was more of a curve in between that. You see what I mean? Like X
Like
squared.
it went back up more?
Yeah, like went back up more. Would you still use that same left endpoint? Because your bar.
Yeah, that's what left endpoints means. I'm not trying to take anything particular as regards the curve. I am arbitrarily selecting to use the left endpoint of each subinterval to be determinative of what the height of that particular rectangle is going to be. That's it. Totally arbitrary. Picking left ones. Yeah.
I feel like he asked this, but I'm not sure.
Yeah.
We have to pick the number of subintervals, or is that given to us?
It'll be given to you.
Okay.
Most likely, I can't think of a case where you have to pick yourself.
Okay.
All right, so whereas in this particular picture, it's good to start thinking this way, that these three rectangles are overestimates of the curve, right? And they're into the curve. The last one is a slight underestimate. Its rectangular area is below the actual area under the curve for that interval, okay? So in general, these will cancel out and give you a better approximation when that happens. But sometimes you'll make over approximations for every single rectangle. It's fine, just play this sometimes, or they'll all be underestimates, right? Doesn't matter. Just do whatever you're told in the textbook. I'm going to show you what it means to be a left endpoint as well as a right endpoint. All right, so now I'm going to write out a formula for the sum of these four rectangles. So that we'll have a formula we can use anytime we want to use a left endpoint approximation. I've chosen 4 here for n, but we can take the 4 out and replace it with n in a second if we have to. All right, so let's see. Delta x is the width of every single rectangles, and I have 4 of them. So what I need is area of rectangle 1 plus area of rectangle 2 plus area of rectangle 3 plus area of rectangle 4. And I need to write it in mathematical notation. That's obviously what we're doing, right? We're just going to add these 4 rectangles together, the 4 areas. So what is rectangular 1's area?
Delta x times f of a.
That's right. I'm going to write it the other way, but you were correct. F of a delta x. Delta x is the width of a rectangle. Every rectangle is width times height. So this is the glory of choosing equal length subintervals. I know the width of each one already. Every area that I'm adding together has the same width, delta x. Okay? Plus, what is the area? Well, it's going to be something times delta x, and it's determined by the height at this location, right? So what is the x value here that I'm putting into said function, right? That is f of something. In terms of our notation, it's f of what?
Is it f?
What x though?
A plus